Thank you for giving me the opportunity of presenting our latest and largest project. It just started a few months ago. So I would like to present more the motivation and the concept of the whole project on what we plan to do, rather than come up to you with results. The detailed name is Novel Evolutionary Model for the early stages of stars with intelligent systems. And this, of course, has to do with star formation, which is my main research field. And star formation star formation not only produces beautiful images like what I show here on the left-hand side. This is a protostar, class 1 object, as we coin them, showing these large dynamic structures, which are protostellar jets interacting with their environment. Star formation links actually very different scales from the formation of the evolution of gas into galaxies. So the cycling of matter and the evolution of galaxies, as it is recorded in this Schmidt-Kennicut law, to the shape of the initial mass function. So the shape and the distribution of stars to the different mass beams, which is decided during the fragmentation and the early formation of stars. And of course, to the formation of planets that we now are aware of a large number of exoplanets being around a vast majority of stars, a few thousand already. And of course, the conditions for habitability, the conditions for accreting the first atmospheres actually are related with the formation of stars. And to end, it of course links to the formation of the solar system as we understand it, to the chemistry and the chronology from the chondritic material in meteorites and these CAIs, the earliest solids. So we studied them in the labs. So star formation has been developing together with the evolution and the development of infrared, mid-far infrared and sub-millimeter facilities over the last 40 years. And actually the beginning of what we understand as the classification of young stellar objects comes shortly after the first infrared all sky survey with HelAS back in the 80s. HelAS was a short-lived mission back in 1983. It lasted just for 10 months, but the impact to astronomy was very large. It was huge, actually. And just a few years later, after the first photometric catalogs from HelAS were published, we have this paper which proposes that stars form and evolve in a series of classes, starting from the class 1 phase. A class 1 phase is a very cold object surrounded by a dense envelope of gas and dust, which eventually is consumed the envelope, and you go to the class 2 phase. The class 2 phase coincides actually with the known at the time Titori stage. And then you move up to even more involved sources with anemic disks, which presumably at this phase, planets were expected to be forming. The development of sub-millimeter facilities at the beginning of the 90s, end of the 80s and beginning of the 90s, we managed actually to observe an even colder and more embedded class of objects, which is now coined the class 0 phase. And together with the understanding that these objects, they push material outwards in jets and outflows, and linking the protostars with the known from the 50s Herbig-Haro objects, led actually to the solidification of a very concise image of how these objects form. So we have these 4 classes, from class 0, the more embedded protostars, to the class 3 objects that are surrounded by thin disk. And presumably, the accretion of mass onto these protostars is a continuous process. They're fed up with material at a much higher rate, at a much faster rate when they're younger, at the class 0 phase. And when they cross from one class to another, the accretion rate presumably drops by about an order of a magnitude. Conversely, their lifetimes of these different stages are going the other way around. So when you go from one class to another, then the protostar stays in that class for about an order of a magnitude longer. And the basic classification criteria are shown lower panel, we believe that there is an evolution of the different components, which is the central source, an infrared disk, which is surrounding the star. And when we study the formation of planets, the formation of planets are presumably starting as a consequence of star formation, but at the end of the process. So you first form the protostars, and then at the end of this process, with the remaining material on the disk of the class 2 objects on the T-Tauri stars, you need to wait a few million years so that through collisions, you can create larger and larger conglomerates of material that they will form eventually planets. So this classification scheme has been, it's actually what we use still today. It's been quite old, but it has a few drawbacks. To begin with, if you observe these objects at different inclinations, then you can very easily now have changed the lower panel. You can very easily confuse an edge-on class 1 object for a face-on class 0 object. And the same is true for a class 2 and class 1 object. So misclassifying these objects just with, when you observe them at different inclinations is quite easy. Moreover, the assumption that accretion is a smooth and continuous process is no more valid. We know that these objects, they're variable in accretion, and actually variability might be may take eruptive forms. They may be associated with the classes of the eruptive variables, the evolutionary objects. They're supposedly located between the class 1 and the class 2 phase, or the EX loop, EXOR objects, which they have longer and lower, shorter time scales, and they can produce increases in their total luminosity by a few orders of magnitude. And then, of course, related to variability and variable accretion, one of the interpretations is companions, is multiplicity. And now we know at higher angular resolutions that these objects, especially when they're younger, they may form in multiple systems. So all this information that we understand now better may lead to a misclassification. So when we try to plot these objects, these different classes, in diagrams that they resemble what would be a color magnitude diagram for normal stars, it is hard to read a definite evolutionary pattern. And we believe that the main reason for that is that we do not classify them properly. Not only that, timescales for the evolution of different objects are based on number statistics. So when we have erroneous number statistics between the different classes, then the timescales we assume or we measure for the evolution between the different classes is also wrong or not so accurate. So this has been now supported by many more observations. So when we observe T-Tauri stars, these are the sources that they have already consumed their envelope material. We can access their disks directly. We can see that these disks are carved with these concentric dark cycles, and these are locations where planets form. And this, of course, to the standard scenario is okay. It's fine because these objects, they are there for about 10, 15 million years. These are two examples here. They all appear to have these concentric cycles. However, there's been one observation at the largest angular resolution we could reach with ALMA in 2015. And this is HL tau. HL tau is a class 1 object, or borderline class 0, class 1 object of just 1 million years. And it appears that planet formation actually is happening much earlier than we previously thought. And of course, the conditions for these planets, the material they create, it's much different because these are the embedded disks. They have a very different chemistry and a very different composition than the evolved disks we observe on the left-hand side on the more evolved sources. So this is, of course, confirmed by gas observations. Gas actually shows that these gaps are not only some instabilities, but they're related, they're sinking points that actually accrete primordial atmospheres in these early planets of those disks. So today, we have enhanced significantly higher quality and much larger volumes of data and much more advanced computing methods. So we believe we can do much better. And the way to do much better because of the volumes of data we have in our possession is with automated ways. And here comes machine learning techniques to play a major role on that. And that's the basic concept behind NEMESIS. With NEMESIS, we'd like to use machine learning methods and techniques and use all the data that we have acquired from the times of HelAS. And we have many missions and many all-sky surveys, and combine all this data to understand better how star formation works, the relevant timescales. So let me just visualize this, how the data we have in hand today can actually show how star formation works in a star forming region. And this is very well studied star forming region, NGC 1333. This is a color composite image of mostly visual filters. And much of the happenings in the star forming region is hidden behind dense clouds of dust and gas. When we go to the mid-infrared observations, this is Spitzer color composite image. We can immediately see the star formation in the making. All these green snake-like features emanating from these young stellar objects. These are jets and outflows. They produce a very rich chemistry, and they actually induce turbulence into the star forming region. And then when we go to even longer wavelengths in the mid-far infrared, this is color composite Spitzer and HelAS image, then we start taking and observing the colder components, the youngest stars, young stellar objects in the star forming region. And you can already see their colors there. So we believe already that far infrared colors can provide a much better discriminant for the embedded protostars to study, to classify them, rather than using the near infrared colors as it has been the case until now. And of course, as we go to longer and longer wavelengths, resolution, of course, drops in a single dish telescope from space. But then we can go, but you can already see the structures connecting these sources to the larger scale filaments in the molecular clouds of the dust emission. But these wavelengths we can eventually reach from the ground. And of course, now we have, as I showed you before, ALMA and other interferometers, and we can study directly the multiplicity of those sources. So all this information can be put together. We plan to make the largest coherent panchromatic WISO dataset for all nearby star forming regions. We're interested in low mass star formation mainly. High mass star formation can be a small part of the project towards the end of the project. We're interested in not only producing the SED. On the right-hand side, I show a few examples of T-Tauri stars, similar panchromatic data collections we had for a different project in the past. We're interested also in line emission, which is may give information about the chemical evolution of these objects. When data are not readily available from past missions, for example, the HelAS catalog, we plan to create such catalogs by using machine learning techniques. So we plan to reduce all the observations. Yes. Coming from these objects, I'm very close to finishing. And then we will use machine learning techniques, supervised machine learning techniques, to create an unbiased WISO classification, and then unsupervised techniques to actually try to figure discriminants, classification criteria that they can tell us better how these sources evolve. And of course, at the end of the day, we'd like to know about the variability and multiplicity. So last slide before closing, who we are. NEMESIS is a Horizon 2020 project. It has secured additional funding from the Austrian Research Promotion Agency. The team is shown in the right-hand side. That's our meeting when we were preparing the proposal pre-corona times, February 2020, before the first lockdown. On the left is Gabor Martin from the Concoli Observatory. He's a specialist in machine learning techniques, applying them in reducing data. At the center is Marco Dart from the University of Geneva. And then on the right-hand side is myself. I'm leading the project at the University of Vienna. We will have soon 3 postdocs and 1 PhD student hiring. We're hiring now. So we have a couple of positions which are still being negotiated. If there is anyone interested, or if you know students would be interested, especially in working with machine learning techniques in large data samples, we're interested. And we may be compact as a group. and we have a significant funding in our hands, but it's not only us. We already create an extended network of collaborators. We have secured an easy teams for 2021 to create a group. We're already 8 scientists there. We'll be organizing meetings starting from next year on how we can deal with the big data and star formation studies. So if you want to follow us, at the bottom, I give the address, nemesis.univ.ac.at. And thank you very much. If you have any questions, I would be happy to answer.
Thank you, Odysseas. Now, please, if you have questions, we can, I'm sorry. Okay, so if you have questions, please unmute yourselves and or raise your hands.
Hi, Kostas, if I can ask something.
Yes, go ahead.
So, hi, really nice talk. I would like to ask something with respect to the machine learning part. If you have any idea of what is the features that you're going to use, is it going to be photometry?
It's going to be both. So it's starting with photometry, starting with the shape of the SCD. So how these objects seem to evolve, how they consume, and how the different features in the dust emission change over time. But it's not only that. Then it's going to be line emission. That's coming in about a year from now. So line emission, there are specific classes of objects that we do not know exactly how they fit in the whole image. One of these is called the hot corinos. Hot corinos are presumably very young stellar objects, and they show something very particular. They exhibit a strong emission of what we call complex organic molecules. So these molecules, apparently, they're not at the same abundances. They don't appear to be in place at more evolved sources. So chemistry seems to be an important discriminant in the evolution of these sources. And we plan to use chemistry as well. But that comes as a second stage.